Hello, everyone. Thanks for joining. So I'm going to start off by talking a little bit about the kind of research we do at Columbia and how it relates to science. Mostly at Columbia, we work more at the network level, so we are more of a systems level integrator almost for science. So a lot of the technologies that's developed at the other partner universities, we then bring it to Columbia and insert it into a test bed, and once we do that, we have to come up with smart, intelligent control around the technologies developed so they can go from functioning as a standalone unit to actually working in a network. And this work, which I presented at Photonics and Switching earlier this summer, is a great example of a collaboration between people who develop devices within CIAN and how we insert it into the test bed. So this work is done in collaboration with Professor Wilner's lab at USC. They develop optical OSNR monitors, which is optical signal to noise ratio monitors. And they've done a lot of work on this, and it's a very versatile device. But most of their work has been on standalone characterization of the device itself. And what we did was we put it into a test bed, and once you put it into a test bed with different kind of signals, we realized there are challenges to that. And the work here is basically looking at how you overcome these challenges in a real test bed. All right. So the motivation for why we are looking into dynamic optical networks, which most of you are familiar with anyway, is the fact that traffic patterns are becoming increasingly more and more heterogeneous. One of the reasons for this increasingly heterogeneous traffic is moving forward, most of the traffic is coming from the metro area. As you can see, by 2017, the traffic from metro area will actually exceed the traffic from long haul. And since metro area traffic comes from different point-to-point connections, different enterprises, different households, it's a very heterogeneous, bursty mix of traffic. On top of that, what we have is emerging applications such as e-signs and grid computing and online gaming, and all of these are causing traffic flows that are very high bandwidth and very short-lived traffic flows. So the result of this bursty traffic can be seen in this slide. For example, you can see the difference between the busy hour traffic, which is basically when you have a sudden demand for bandwidth, versus an average hour traffic is increasing over time, which proves the fact that traffic is becoming more and more bursty over time. This is a problem because today's networks are mostly static. So our network is basically designed to handle the peak hour traffic, which is over here, although most of the time during the day, what you would be serving is a traffic that is down here somewhere. So as a result, you have a lot of this much of wasted capacity, and all of the network devices are sitting idle and powered on throughout, wasting a lot of energy. So one solution to this is a dynamic optical network. So we're defining a dynamic optical network as one where bandwidth is allocated on demand in the physical layer. However, this would require decreasing light path setup times from order of days, which is what it is today, to the order of minutes. And this comes with multiple challenges, the most important of which is EDFA transients and other associated impairment, transmission impairments. As a result, a dynamic optical network is very hard to predict and very unstable. So one way to actually have a dynamic optical network that can provide customers with the services that they require in a stable fashion is to have ubiquitous optical performance monitors distributed throughout the network. Through this, we have real-time knowledge of the state of the physical layer, and we can make intelligent resource allocation decisions to counteract any instability or any impairments that we caused by doing dynamic control in the first place. So one of the promising solutions for distributed OSNR monitoring is the delay line-based interferometer technique, which was developed at USC, as I mentioned before. The reason why this is so great is it's cost-effective because it can be integrated on silicon photonic platform, and I believe people at Cornell have done some initial fabrication showing that this is possible and this can be done in-house through CIAN. It supports multiple modulation formats and bit rates, and including polarization mux data. The biggest drawback, however, is that it's dependent on data rate and modulation format of the signal under test. So given that the next generation network is going to be supporting mostly metro area traffic, it's very likely that it will be operating with both mixed data rates and modulation formats. There hasn't been a lot of publication showing that having mixed line rates is the most cost-effective method of transmission, especially for shorter distance transmission. So in order to actually use this device in such a next generation network, the DLI has to be able to distinguish the signal characteristics of the signal that it's monitoring at any given time. So what we are proposing is using low frequency pilot tones to almost act as a signature for the signal under test. So basically what we're adding is a small amount of sinusoidal modulation on top of the signal itself. But as you can see from this diagram, you can go up to modulation indexes of 12% without really affecting your VER of the signal itself. So this has been extensively studied in the past, and it's a pretty well-established technique. And now we're just putting it on top of our transmission system to act as an identifier. For us to be able to detect the pilot tone at any monitoring point, we basically just look at the RF spectrum of the signal. So if you're looking at an RF spectrum without a pilot tone, basically you will get the clock tone of the signal, which is the data rate of the signal. But if you have a pilot tone embedded on top, then you'd get an RF frequency spike at your pilot tone frequency. For example, if my pilot tone is 10 megahertz, then I will get a power spike at 10 megahertz. And the idea is that for each different signal, you have a different frequency pilot tone. So this figure shows the modified structure of the DLI monitor that we use to be able to detect the pilot tone. We use a simple DSP unit that processes the outputs from the two photodiodes at the DLI and extracts the pilot tone frequency along with the powers at the two different ports, which the powers are actually used to measure the OSNR of the signal. So one of the concerns here is that the DLI to start with is very sensitive to the modulation format, and we are adding pilot tone is essentially a small amount of modulation that we are adding on top of each signal. So we need to ensure that it's not affecting the OSNR to the ratio mapping of any given signal. So in order to establish that, we looked at 4 different types of signals, 10 gig OOK, 10 gig DPSK, 40 gig OOK, and 40 gig DPSK. And for each signal, we looked at the case with a pilot tone and without a pilot tone. And we plot the worst case discrepancy in both cases, both sets of results that you see here, which is using a pilot tone of 0.0 30% modulation index or 0.3 modulation index pilotone. And both from experimental and BPI simulation results, you can see that with and without pilotones, the results are almost identical, establishing that the use of pilotones is a valid method to identify signals. So once we validated that pilotones could be used, we wanted to put this in our real network and validate its performance. So this is the picture over here is an architecture of the network that we envision once we have the pilotone in place. So what we are proposing is by using a pilotone, each monitor can operate locally at any given node. It has its control plane that's basically associated with the node itself. It doesn't need to communicate to the unified control plane to ask what kind of signal am I monitoring, what's the modulation format, what's the data rate. Everything it needs to know about the signal, it can find out locally. As a result, it can do all kinds of monitoring on its own without having to talk to the unified control plane. And this is good moving forward because this reduces the amount of signaling that's required between the unified control plane and each of the individual nodes. And also it's good in case something went wrong in the unified control plane and it starts disseminating wrong information, or if a node loses signaling between the control plane and itself, it's not affected. It's still able to function and make all the decisions that it is supposed to independently. So keeping in mind that this is the kind of network that we are trying to build up, I'm going to go to the next slide, which shows us the actual network that we built up in lab. So this is a cross-layer testbed because we're using measurements in the physical layer to control, to affect performance in the higher layers. So again, we used 4 different kinds of signals: 10 gig OOK, 10 gig DPSK, 40 gig and OOK, and 40 gig DPSK. Each signal is given its own unique pilotone, and then they're muxed together and injected into the testbed. So this, the distance emulator portion of the testbed basically emulates a mesh network that we show on top. So here, using WSS1, we can either send the signals along an impaired path, which is the one on top, or along a good path. And then at WSS2, we combine the signals coming in from different sources and then finally send it on to our last receiving node. So at the receiver node, the signal coming in is, portion of the signal coming in is tapped and divided and sent to the OSNR monitor. And at the OSNR monitor, again, part of the signal is actually sent to the DLI to measure the constructive and destructive powers. And the other portion of it is sent to the photodiode connected to an RF spectrum analyzer so that we can identify the pilotone and hence the signal under test. So we looked at, to validate the robustness of this monitor, what we did was we studied its behavior in the worst crosstalk signal configuration. And this was a concern because when you're basically taking a pilotone from your signal, but if your neighboring signals have different pilotones and it's leaking into your main signal, at what point do you start seeing at what point does your crosstalk signal power, crosstalk pilotone become the more dominant one? Is that going to cause erroneous identification of signals, for example? So since everything we did was on a 50 gig ITU grid, which means the channels are very closely spaced, and crosstalk is a big issue in such cases. So in this case, as you can see, the blue dots show the pilotone power of the channel that we are actually monitoring, and the red dots is due to the crosstalk from the neighboring channels. And we can up to negative 13 dBm of power at the receiver. The channel pilotone is still the dominant one. And this is using just raw RF power that we measure at the RF spectrum analyzer. So another way of looking at it would be to use the signal-to-noise ratio instead of the raw RF power, because this will take into account any characteristic noise floor slants of the photodiode. And once you take into account of that, we see that we are actually able to detect the correct channel pilotone up to negative 18 dBm of power. So this set of results show that what happens when you have a very high OSNR, very high power neighboring channels, and the OSNR of your signal that you're actually monitoring is changing over time. So as your OSNR degrades, does the quality of your pilotone detected also degrade such that your crosstalk pilotone become more powerful? And as we can establish from this figure, that is again not a concern that we have to worry about, because at low OSNRs you stop detecting the crosstalk pilotone at all. As you can see, below 15 dB of OSNR, there is no crosstalk pilotone. So again, this establishes that we don't have to worry about crosstalk. And then we move on to the last set of readings, which was something we accidentally discovered, actually, was what's the effect of all these crosstalk on the DLI readings? So as we discovered, having crosstalk from neighboring channels actually affects the DLI mapping for a signal. And this can result in erroneous OSNR calculations if you don't take into account for the fact that you're getting crosstalk from neighboring channels. So the crosstalk tone that we are getting is almost now a good thing, because now it tells you that, look, I'm monitoring a signal, I'm getting a crosstalk pilotone, which means I'm getting crosstalk from neighboring channels. This is the kind of channel that I'm getting a crosstalk from. So you not only know what your signal type is, you know what are the signal types of your neighboring channels, and using all this information, you can then correct for the effect of crosstalk on your DLI measurements. So you get your correct DLI measurements and correct OSNR measurements, and then you also are able to detect for crosstalk in your network. And if it is to a point where it's extreme, you can ideally start taking corrective measures to take care of that crosstalk as well. So in summary, in this work, by using pilotones, we have allowed the DLI-based monitor to work in a next generation network, which will ideally be operating in mixed modulation format and bitrate formats. We have established the robustness of our pilotone system and demonstrated that crosstalk is not an issue. Having the crosstalk pilotone is actually an indicator of the strength of crosstalk and will allow our monitor to function even in presence of high crosstalk. And as a result, it allows autonomous signal quality decisions anywhere in the network, simplifying the structure of our centralized control plane. I think that's all I have, and I guess I'm open for questions. Thank you.